happens when you have collisions in 2 dimensions. So far we've been studying one-dimensional problems. A car is on a track, it smacks into another car in the same track. It's a head-on collision. Okay? Sometimes we call collisions in 2 dimensions, we call them glancing collisions. So if a billiard ball doesn't hit the next ball smack on, but hits it a little bit at the side, they both go off at an angle, right? So we call these glancing blows or glancing collisions, or just collisions in 2 dimensions. Those are all words that mean you're going to have to worry about more than one dimension. All right? So, that was the warm-up. Here's what you got. If there's no external forces, then the change in momentum is 0. But what does that little line right there mean? It means it's a vector. And if it's a vector, then you know that if an equation is a vector equation, then that equation must be true in any direction. Okay? Quick reminder, back when we were solving problems with forces, you might have had a force going this way, like a tension T1. You might have had a tension going this way, T2, and a weight going here, mg. We said that the net force was equal to 0. The force is a vector. And that meant that the net force in the x direction had to be 0, and it had to be true in the y direction, right? Remember that? So if a vector equation is like this, it's true in every direction. So if the momentum equation, if momentum is a vector, then this must be true in every direction. So that means that the final momentum must equal the initial, oh, it should be initial momentum. The final momentum should equal the initial momentum. And since that's a vector equation, it must be true in the x direction, and it must be true in the y direction. Okay? So the fact that this is a vector equation tells us that momentum must be conserved in all directions. So I'm going to solve an example problem of how we use that. All right, so all I'm doing is saying, if momentum is conserved, it's conserved in every direction, not just the x direction. Okay? So here's the example problem I want to solve. I'm going to move the screen so I can just write on the board. Stop right there. So here's what happened. Can you guys read that?
No.
Need another 7 You don't want to laugh at it.
No.
Oh, well, close enough. Here's what you got. You got a marksman with an arrow. They fire the arrow in the positive y direction as a target comes sliding across the x direction. The arrow smacks into the target, embeds in it, and the two of them slide off in that direction. And I want to know, what is the velocity of the pair, and what angle is the pair going at? Okay, so we're going to try to find this angle right here. So to do that, we're going to apply the vector nature of the momentum equation. There are no external forces. It's sliding on ice, and you're the bird looking down on it, right? So there's no external forces, which tells us that P final must equal P initial. And that's a vector equation, which means that the momentum in the x direction final must equal the momentum in the x direction initial. And it also must imply that the momentum in the y direction final must equal the momentum in the y direction initial. Okay? So we're going to get 2 equations out of this. Now, what's the x and the y direction? Not a trick question. I can't talk about x and y direction unless I define a coordinate on my diagram, right? Which way should the x direction go? It doesn't matter, but pick it so your life is easy, right? If you decide to make this the x direction, then both of those guys are moving in some weird angle. So let's just make this the x direction, so the target's moving in the x direction. Let's make this the y direction, so the arrow's moving in the y direction, and then that thing goes off at some goofy angle. Okay? Doesn't really matter, you can put the coordinates anywhere you want. In fact, make your life easy by putting them so that as many possible objects are on the axes as possible. Okay, so this thing goes flying off in this direction. It has some final velocity, and so its momentum is going to be the mass of the arrow plus the mass of the target times its final velocity. Right? Momentum is mass times velocity, right? So this is its mass, and its velocity is v final, and it's going at some angle theta. So, in the x direction, what is the initial momentum in the x direction? What has momentum in the x direction before the collision? The target. And so how much momentum will it have? Mass of the target times the velocity of the target initial. And we happen to know that, right? The mass of the target is 1.2 kilograms, and its velocity is 5. We know those two things. What's the final momentum here? That's the final momentum going in that direction. What is its x component? How much of it is going in the x direction? So if this is the final momentum going that way, we want the x component of the final momentum, this component. So that's going to be the mass of the target plus the mass of the arrow times the final velocity times the cosine of the angle. Okay? All right, so what do we not know in this expression? What is unknown? Help me here. Tyler?
Angle?
We don't know the angle, and we don't know the final velocity either, right? There's two unknowns. What do you need if you got two unknowns?
Second
You need another equation. Where do you get another equation from?
The y side.
It's y problem. The final velocity in the y direction is the mass of the target plus the mass of the arrow times the final velocity times the sine of the angle. That equals the initial momentum in the y direction, which is what, Mr. Kelly? What's the initial momentum in the y direction?
The arrow. The mass of the arrow times the velocity.
The mass of the arrow times the velocity of the arrow initial. And again, we don't know theta, and we don't know v final. But now we have two equations and two unknowns. So how are you going to solve for theta and v final? Any ideas? We've got two equations, we've got two unknowns. What the heck are we going to do with them? Solve them both for v final and theta equal to each other? That's how you want to go? That's what you said. All right, so Josh is going to solve them both for final velocity here, right? Okay, so here we're going to get final velocity equals mass of the target, velocity of the target initial, divided by mass of the arrow plus mass of the target times cosine theta. Now, it doesn't really matter. It turns out it's slightly easier, but not much, if you substitute that in here, as opposed to solve this also and then equate it. Okay? Just because you're going to see a trick that you may not see otherwise. If I substitute that in here, I'm going to get mass of the target plus mass of the arrow times the final velocity, which is mass of the target, velocity of the target initial, all over mass of the arrow plus mass of the target times cosine theta. So that's my substitution there. Times sine of theta equals mass of the arrow, velocity of the arrow initial. So what simplifies?
The MC plus MC.
Yeah, the combined mass cancels that and that. Yeah, sine over cosine is tangent, and that's what we need. So we're going to get the mass of the target, velocity of the target initial, that's that, times sine over cosine, which is tangent of theta, equals mass of the arrow, velocity of the arrow initial. And so we can then say the tangent of theta is the mass of the arrow, velocity of arrow initial, divided by the mass of the target, velocity of the target initial. And so how do you find theta? Go ahead. Grab your calculator. You can walk right now. Oh, come on. Arrow. 65 times 21, so this is 6.5.
Yeah, but I don't know
1.2 times 5 is 6. So the arctangent of 6.5 over 6,
47.
that's slightly bigger than 45, so I'm going 48.
47.2.
So the angle theta is 47.2 degrees. Once you know theta, how are you going to find V final? Back substitute, right? You've already found V final in terms of theta. So take your answer here, plug it in there, and you can find your final velocity. Go ahead. Try it. So when you back substitute, the final velocity is what, Ben?
14.
No.
6.1.
Go, calculate
So
it.
close.
Theta's 47.2, plug it in there. What's the cosine of 47? Pretty
6.8.
darn close to 1 over the square root of 2?
6.8.
Yeah.
6.8 meters per second. So the combined target is moving 6.8 meters per second at an angle slightly bigger than 45. Okay? Now, one of the things you'll see on the AP exam, you might be asked to, without solving the problem, just based on the initial problem, to determine whether the angle that it moves off at is bigger than, less than, or equal to 45 degrees. And that's not terribly hard. How much momentum does it have initially in the y direction? What is that? 6.5 units of momentum in the y direction. How much momentum does it have in the x direction? 6.0, right? So what's the final momentum in the x direction? It's 6. What's the final momentum in the y direction? It's got to be 6.5. That angle is going to be slightly bigger than 45 degrees. Right?
Yes, that makes sense.
Okay. So, we are not going to solve problems. All the problems we're going to solve involving two-dimensional collisions are going to be hit and stick. Okay? Life gets really ugly when you have elastic collisions in 2 dimensions. You get 4 unknowns because there are 2 objects in motion, so you don't know their velocities or their angles. There's 4 unknowns, you got to get 4 equations. It gets ugly. We're not going to do those.
Bonus problem?
No, well, I got a bonus problem for you. It's not that.
Give him ideas.
So,
Wait, hold on. Elastic?
what?
Elastic don't stick, or does stick? What?
Elastic doesn't stick.
Doesn't stick.
Energy is conserved. Hit and stick is a special case of inelastic. So, if you have elastic collisions, you get 2 equations. One from momentum, one from conserving energy. If you have 2-dimensional problems in this course, you get 2 equations. One from the x and one from the y problem. Okay? So, to practice this, homework 4 is waiting for you. Oh, you're welcome.
Thank you.